Hi there, welcome to Lesson 14, Linear and Exponential Models, Comparing Growth Rates. So we're going to start with example 1 and linear functions for this video. So for linear functions, sketch points P1 and P2, which is 04 and 412. Are there values of m and b such the graph of the linear function described by f of x equals mx plus b contains those points? Well, let's understand a few things here before we start. So m, that's going to be my slope. I always know that. And I know that b is my y-intercept. So what this is basically saying is, given these 2 points, P1 and P2, is there a slope and a y-intercept that allows me to have to put it into y equals mx plus b form? So let's go ahead and do the step 1. Let's just draw the thing out. So let's go ahead and draw this here. I know I'm going to go to 0, 1, 2, 3, 4, and we'll go ahead and do P1 in red. So that is the point 0, 4, and that is P1. And I know I'm going to have to go up to 12 for P2, so 5, 6, 7, 8, 9, 10, 11, 12. And it's at 1, 2, 3, 4. So let's go ahead and do that one. Let's go ahead and do that one in blue. So now I've got the point 4, 12, and that is P2. And what's asking me is, again, I'm trying to find a line. I'm trying to find, oops, that did not quite hit the points. There we go. I'm trying to find a slope and a y-intercept for this line. But this is already really easy for the first part. I already have a y-intercept. I already know that 0, 4 is at the y-intercept. Remember, the y-intercept is where the line intercepts or connects with, crosses the y-axis. So I know that at the point 0, 4, so at b equals 4, y value of 4, that's where my y-intercept is. So y equals mx plus 4. That's what we already have so far. So now let's go ahead and try and find that m value. So in order to do that, we can do this multiple different ways. We can do this algebra. So I know that m, my slope, is the change in y over the change in x, which is the same thing as y2 minus y1 over x2 minus x1. And remember, I know this because this second point minus the first point will get me the slope between them, right? It's the y minus the y over the x minus the x. And I always take the point that's farthest on the right minus the point that's farthest on the least. So by doing this, I get the points. Well, y2, the y value of 0.2, is 12 minus the y value of 0.1, which is 4, over 4 minus 0 will give me 8 over 4, which is 2. So I already know m equals 2. So y equals 2x plus 4. Now we can say we're done, but let's go ahead and look at this one more time with algebra, or with geometry. So I know that this has an x value of an x distance of 4 and a y distance of 8. So again, slope is just y over x, rise over run, which in this case is just 8 over 4, which is also 2. So we can find the slope using algebra or using just by looking at the graph, using a little bit of geometry. So let's go ahead and move on to the second problem. For sketch P1 and P2, let's just go ahead and do that. Let's just go ahead and sketch that. Let's go ahead and 0, 1, 2, 3, 4. We'll go ahead and just do this one in red as well. So 0, 4, and that is P1. And then we'll go ahead and do -1, -2. That one is 0, -2, which is P2. Let's go ahead and erase this random guy over there. And hold up, I see something interesting. So this is also asking for a slope and a y-intercept so that the graph of the linear function the linear function described by this. So again, I am looking at a function, but I noticed something odd about my graph because functions have certain rules that they have to follow, such as every input can only have one output. And here I see I have, whoops, let's not use that. Let's use, I have the point 0, comma 4 and the point 0, comma -2. And I see that these have the same x value and these have different y values. So I already know that this can't be a function. It breaks the rules of what a function is. Also, I can do my favorite test, the vertical line test. And notice it passes this point and this point, which since this function, since this line, this graph breaks the vertical line test, I know it can't be a function. So that gives me my answer already. So I'm going to go ahead and do the second part of if not, which it's not, explain why they do not exist. Okay, well, there is no function, so not a function. And because, and we could use either way. We could say vertical line test, or we could say, let's just go ahead and put the algebraic one, because there are multiple y values, multiple outputs, multiple y values for the same x. Whoop, where is my red? There we go. X value, which breaks a function. Also, I can look at this in terms of geometry. So, or let's go ahead and do so. Or for the reasoning, or does, well, it does not look right. Does not pass the vertical line test. And let's go ahead and erase this little guy right here. There we go. So, because it does not pass the vertical line test and there are multiple y values for the same x value, this is not a function. And this wraps up this video. We'll go ahead and go into exponentials for lesson 14 in the next video. Okay, welcome back. Let us continue on. So we are dealing with exponential functions. We dealt with linear functions on a and b in the last video, and here we will be solving some exponential functions using the following two graphs. So, using g of x in our first one, let's go ahead and look at our points. So, just to read it off, we want g of x equals ab to the x. Let's start off with that. G of x equals ab to the x. And if we recall, this is already really easy to figure out. A is our y-intercept. And I already see that my y-intercept is labeled right there. So before I even write anything, I know that a is already equal to 2. I didn't even have to do any math on that yet. So now let's look at our 2 points, 0, 2 and -2, 1 over 2. Now, how can we go ahead and figure out this b right here? Well, I know that g of x equals ab to the x. Well, that's my dependent variable, my y, which is the same thing as the function dependent on x, equals a b to the x. So in this case, I know since y equals a b to the x, there we go, then I can go ahead and use this second coordinate that I have not already used. Remember, I used this first coordinate to figure out that 2, and I can use the second coordinate to figure out b. So my y value right here equals ab to the x value. So let's plug in those y values and x values. I have y value 1 over 2 equals I already know that, 2 b to the x, negative 2. Okay, so let's go ahead and solve for that b. B is the only variable in here, so now I can solve for it. So 1 over 4 equals b to the negative 2, just dividing that other left side by 2. Now, what do I do with a negative exponent? Well, I know that any exponent, let's just say x to the negative 3, I can make that into a positive exponent by just flipping it below the denominator line. 1 over x to the 3. And similarly, 1 over x to the negative 3, I can make that exponent positive by putting it above the denominator line. So let's do the same thing over here. I can have 1/4 equal to b squared. Oh, let's go ahead and rewrite that. There we go. 1 over b squared. Now, we have two fractions here, and I want b squared obviously on the top, so I'm just going to cross multiply to get rid of my fractions. So this is going to be, I'm going to do it up here on the right, b squared equals 4. Remember, we got that by multiplying the 1 by the 4 and the 1 by the b squared. So now that b squared equals 4, this is easy. b equals the square root of 4, which I know is plus or minus 2, but I want only the positives here. So b equals 2. And now that I have a and b, I can just write my answer. G of x equals 2 times 2 to the x. Perfect. Now let's go ahead and move on to the second one. So now I don't have my y-intercept, but I do have my 2 points that I can use. So let's write the left-hand side one first, negative 1, comma 2. And the other coordinate would be 2, comma 27 over 4. Ooh, that's a fraction. That's going to be tricky, but I don't think it'll be a problem. Let's go ahead and do this. I have 2. Remember, this is always y equals a b to the x. So 2, my y value, equals a b to the x, negative 1. Well, that's the same thing as 2 equals a over b. Remember, I can move that b below the denominator line. And then 2b equals a. Now I have a by itself, and this allows me to plug it into another equation. So now let's go ahead and do this other equation. Let's just do it in blue. So using the other coordinate, 2, comma 27 over 4, I have my y value, 27 over 4, equals a b to the x, to the 2. But I have a already. I already know a equals 2b. So I'm going to go ahead and plug in 2b into the a. So then this will be 27 over 4 equals 2b times b squared. And I know 2b times b squared, that's just the 2, and then b times b squared equals b cubed. Remember, b squared is just b times b. B cubed is just b times b, in other words, b squared, times b. All right, perfect. So now let's just go ahead and solve this. So 27 over 4 equals 2b cubed. Well, let's go ahead and get rid of that 2. So 27 over 8 equals b cubed. Remember, this happens when I just divide the 2b cubed by 2. So now I know what to do here. I can take the cube root of everything. Remember, cube is 3. So b equals the cube root of 27 over 8, which is the same thing as, now, whenever I have that root, I can distribute that cube root. So it looks like this, 27 cube root of that over 8 cube root of that. This is just like over here, if I want to show it. If I have 3 over 4 quantity squared, that's the same thing as 3 squared over 4 squared. So I can, just like how I have this squared, and I can distribute it to each of the things inside, I have a cube root, which I can distribute to each of the things inside. And every square root, the square root of x, remember we always imply this little 2, is the same thing as x to the 1 over 2. So cube root of x is x to the 1 over 3, because this is a 1 right here, and this is a 3. So whatever's on the inside right here is in the numerator. Whatever on the outside is in the denominator. This is always a 1. It's an implied 1, and this is a 2. That's why I have 1 over 2. So, coming back over here, what times itself 3 times equals 27? Well, that's easy. I know that that's 3. 3 times 3 times 3 equals 27. And what times itself 3 times equals 8? Well, that's also easy. 2. We're given 2 whole numbers here. So I know A equals 2B and B equals 3 over 2. So, coming back over here, 2 times 3 over 2 equals, and that will be equal to, the 2 and the 2 are going to cancel, so that just equals 3. So A equals 3. So now that I've got all of that, let's go ahead and write the answer in red. G of x equals 3 times 3 over 2 to the x. Now, please be careful about that 3 over 2. It needs to be in parentheses. 3 over 2 to the x is not the same thing as 3 over 2 to the x. Okay, because here on the left-hand side, this is the same thing as 3 to the x over 2 to the x, which is not the same thing as, if I just think of each number separately, 3 to the x over 2. On the left-hand side, because I have this parentheses, I distribute the x to both of them on the inside. So it looks like this. On the right-hand side, I was not careful with my parentheses, so it looks like it's only on the 3. You must have this parentheses. So let's go ahead and move on past that one. So example 2, a lab researcher records the growth of the population of a yeast colony and finds that the population doubles every hour. Okay, that's easy. So I've got 0 and 1, so this is 5. So if it doubles, that'll be 10, double 20, double 40, double 80. Okay, now what do we have to do? What is the exponential function that models the growth of the population, of the colony's population? Well, again, remember, we are going to have an equation of the form, let's say population is P and we're using T, and time will always be my independent variable. So that's going to equal something. That's going to equal some A, B to the X. Okay, well, what is A and what is B? So P of T equals my y-intercept, and I know my y-intercept here is already 5. My y value is 5. So that will be equal to 5 times, and my B is always going to be the rate of growth or a rate of decay for a, so it'll be the rate of growth or the rate of decay for an exponential function. So we see that it is, where is it? It says doubling every hour. So that is the rate. It is doubling. So that would be a 2. And of course, we're just going to write to the x. Oh, that's actually the entire answer. That's it. So now let's go ahead and move on. Several hours into the study, the researcher looks at the data and wishes there were more frequent measurements. Knowing that the colony doubles every hour, how can the researcher determine the population in half-hour increments? And remember, increments just means in intervals type thing. So if we know that it doubles, again, let's just go ahead and write the equation. Oop, not G, it's a P of T equals 5 times 2 to the x, or, whoops, there we go, to the t. Oh, you know what? I'm going to go ahead and erase that in the previous one because my variable is not x, it is t. Be careful about that. Let's go ahead and write that t there. And let's finish that. Okay, so if I have p of t equals 5 times 2 to the t, and I want to know, and t is measured in hour-long increments. Well, I want to go over half-hour increments. So let's just say some random amount x. That is the amount of time in a half hour, right? Well, okay, if I know that the population is 0, at time 0 is 5, and the population at 1 is 10, then I want to find this halfway point. So I want p of 1/2. So I know that 5 times, let's just say, some amount x equals the population at 1/2 hour. So population at a half hour. Okay, so if I take that population at a half hour and I multiply it by another half hour, that will give me my population at 1 hour, which I already know equals 10. So I'm going to have 5x times x, which is 5x squared. So 5x squared equals, well, that's going to be the population at 1 hour, which I already know to be 10. So let's just go ahead and solve for x. X squared equals 2. I'm going to divide that by 5. Whoop, yep. And then x, yeah, so let's just take the square root of it. So the square root of x squared is just x, and the square root of 2 is just the square root of 2. So the scaling factor is root 2. Okay, well, let's go ahead and prove that to ourselves in the next part. So let's explain this real quick. So if I multiply any amount, any population by root 2, I should get the population after a half hour. Well, let's go ahead and fill in this table down here. It's going to double, double, and double. But let's figure out this 1/2. Well, if I take 5 and multiply by root 2, doing it on my calculator over here. So 5 times root 2, and this one should be 10 times root 2, and this one should be 20 times root 2. Well, what do I get? Well, here I get 7.07. And if you need to pause the video so you can go ahead and use a calculator, go ahead and do that. But what happens when I take 7.07 times root 2? 7.07 times root 2. And remember, when you're using your calculator, if you just take 7.07, you might get round off error and get 9.9 something, whatever. So go ahead and take that entire number that your calculator gives you and multiply that by root 2, and you should get 10. So what happens when we take 10 times root 2? Well, let's go ahead and plug that into our calculators over here. And we're going to find that we get 14.14. It'll be 14.1421, but we already know that that's just round off. And for this last part, we'll just be to 20 times root 2, typing it on my calculator, and that will be 28.28. I'm just rounding these off to 2 decimal places. And when we take that 28.28 and we multiply it by root 2, we're also going to get 40. Let's continue on down. How would the calculation for the data change for time increments in terms of 20 minutes? This is an interesting one. So we noticed that when we're up here, and I took it in terms of a half hour, so let's do that. So 5x squared. And that x squared is important because this x squared means I had to multiply this x twice to make 1 hour. So 5x squared, that's 1 hour. Now, if I want to break it into a third of an hour, so 30 minutes equals 1/2 hour. Well, 20 minutes equals 1/3 of an hour. And I think we can already see a pattern that might form here. So if I take 5 times some amount, let's say Q equals 20 minutes. That's the amount of time. So 5Q, well, that'll give me it after 20 minutes. And if I take that amount and I multiply it by Q again, well, that'll be another 20 minutes, which will be 40 minutes. And if I take that amount and multiply it by Q, that'll be another 20 minutes, which would be 1 hour. And this equals 5Q cubed. That's funny. So 5Q cubed. And that one should equal 10. Because again, after 1 hour, I already know that my population is 10. So if I do that, Q cubed equals 2. I'm going to divide by that 5 on both sides. And then Q equals the cubed root, or the cube root of 2, which we know is 2 to the, remember I have a 1 on the inside, so that 1 is going to be in the numerator, over, and that 3 is in the 3 on the outside right here will go in the denominator, so 2 to the 1/3. You can write it as 2 to the 1/3, or you can write it as 2 cube root, so the cube root of 2, and either way will be correct. So explain. Well, I believe we've already explained it well enough using our algebra. Oh, let's go ahead and, nope, yeah, we explained it well enough with algebra. So let's go ahead and finish this table. At 1 hour, I already know it's 10. 2 hours, it'll be 20. Well, this one should be 5 times, oops, don't want a 3 there, I want a 2. I want a 3 on the outside. That's not really a 3. There we go, 3 there. And then this one will be 5 times cube root of 3 times cube root of 3. So let's just go ahead and figure out this number real quick. So 5 times, and if you have difficulty plugging in this cube root on your calculator, you can just do the same thing as 5 times 2 to the, and on your calculator it'll look like this, caret, and then please use a parentheses, 1 divided by 3. Because I know, again, up here, this is 2 to the 1/3 power. So to get that fraction up there, you need to make sure you put it in parentheses. If you do not put it in parentheses, your calculator will read it like this, 5 times 2 to the first power divided by 3. It'll take this entire function up here, or the entire equation up here, and it'll divide it by 3, which obviously we do not want to do. Let's go, oh, that is not an eraser. Here we go, this is an eraser. All right. So put in 5 times 2 to the 1/3, 2 to the parentheses 1 divided by 3, and we will get 6.29961. So I'm going to round that to 6.30. Let's go ahead and fix that. And whenever I take that number and I multiply it by, oh, so this will be 6.30 times, let's go ahead and see 2 to the 1/3. 2 to the 1/3. That one will give me, let's see here, that will give me 7.937. So I'm going to round that to 7.94. And when I multiply that by 2 to the 1/3, I do indeed get 10. And when I multiply 10 times 2 to the 1/3, 12.5992. So I'm going to round that to 12.60. I multiply that by 2 to the 1/3, and I get 15.874. I'm going to round that to 15.87. And if I were going to multiply that by 2 to the 1/3, I would indeed get 20. So let's move on. The researcher's lab assistant studies the data recorded and makes the following claim. That's always a difficult thing to do. Since the population doubles in 1 hour, then half of the growth happens in the first half hour. Uh-oh, I see a problem there. And the other half of the growth happens in the second half hour. Oof, that's not good. We should be able to find the population at t equals 1/2 by taking the average of the populations at t equals 0 and t equals 1. Well, let's figure out what this is asking, well, what this is saying first. That means that if I have some population, let's say 5 in the beginning, then, and this is at, let's go ahead and do the table. So 0, 5, and this at hour 1, I have a population of 10. Let's go ahead and make that a little bit straighter. So this is saying, the research assistant is saying that at 1/2 hour, I would have, where is it right here? At t equals 1/2, I would have the average of the populations. So that means the average of 5 and 10, so 5 plus 10 divided by 2 averages. So that would be 15 divided by 2, which is 7.5. So that would be 7.5. So this is what the researcher is saying. But remember, let's go ahead and look back up here again real quick. I know that that's not necessarily true. At t equals, that's not my pointer. At t equals 1/2, that's not 7.5. That's 7.07, which is not 7.5. So I should be getting 7.07. That one's correct. This one does not look correct. But what is going on? So why is this assistant incorrect? So we have already said that the assistant's reasoning is incorrect. That is not correct. So not correct. But why? Well, this is a very good way of thinking for a linear function, but not for an exponential function. So this is using linear reasoning, not exponential reasoning, not really modeling an exponential function. We cannot model an exponential function by simply taking averages of things, but we could model a linear equation by taking averages of things. In fact, the slope of a linear function, y2 minus y1 over x2 minus x1, is just kind of an average. So let's go ahead and move on. Oh, wait, compare this strategy to your work in parts C and E. And of course, we see that this does not match this, so that's one thing. And 7.94, 6.3, that's not really a whole lot of, that's not helping us a whole lot, but part, C and E. That's right, C. So it should be root 2, not really 1/2. Now let's go ahead and move on down. Example 3. A California population projection engineer in 1920 was tasked with finding a model that predicts the state's population growth. So let's go ahead and highlight this. So in 1920, and he modeled the population growth as a function of time t years since 1900. That since is really important. I'm going to do that in red. And census data shows that the population in 1900 in thousands was 1,490. And in 1920, the population of the state of California was, let's go ahead and do this in blue. So match those two up. So the population in 1920 of the state of California was 3,554,000. He decided to explore both a linear and an exponential model. So let's go ahead and do that. Use the data provided to determine the equation of the linear function. Let's go ahead and, so a linear function that models the population growth from 1900 to 1920. Now, this is a very, very important point here. We are starting in the year 1900. We are starting there. So we're not just going to use 1900 as some x value starting at 0. This is going to start at 1900. So 1900 is basically year 0. So 1900
will be treated as, so that'll be year 0. So that'll be year 0. So we're going to start right there. So let's go ahead and make a linear function. Okay, well, I've got the point 1900, which is again 0, and the point, what is my y value for that? Well, let's go ahead and look over here. So in 1900, I had a population of 1,490. 1490. And in 1920, so 20 years later, I had a population of 3,554. Perfect. So linear functions are always looking like this. So f of x equals mx plus b. And let's go ahead and make that x a little bit better. There we go. So if I want to find b, and I know that I'm using the year 1900 as my year 0, let's draw that. And this will not be an accurate graph, but we can kind of look at it like this. That'll be 20, and this will be 0. And this 1900 is this one, and this 1920 is this one. And of course, this will be at 1490, so 1490. And this one will be at some point right there, 3554. Now this graph is not accurate or not to scale, so just go ahead and understand it from the way that it looks. So I see right here that this is essentially my y y-intercept. So I know that b equals 1490. That does not look like a 0. There we go. 0. 1490. Okay. So if b equals 1490, I have y equals mx plus 1490. And I want to figure out this m right here. Well, to figure out m, I need to find the slope, which m is slope. So I need to figure out this amount right here. Well, I can just do that easily. That's just y2 minus y1 over x2 minus x1, which is equal to, well, the y value of my point 2 of my second point is 3554. 3554. And the y value of my first one is 1490. 1490 over, and then my x values are going to be 1920 and 1900, or in other words, 20 minus 0. And that will give me, what is 3554? 3554, not divided, minus 1490 will give me 2064 over 20. So what is that? What is this divided by 20? Well, that will equal 103.2. Let's go ahead and put that down here. 103.2. So that's what m equals. And I already know b, which is 1490. So in that case, I know f of x equals 103.2 x time or plus 1490. And there we have it. That is the linear function. Now let's go ahead and move on down here to the exponential model. So use the data provided in your calculator to determine the equation of the exponential function that models the population growth. Well, perfect. That's easy to do. G of x, let's not use red there. G of x equals ab to the x, which in other words is y equals ab to the x. I already have my 2 points up here, 1900, 1490, and 1920, 3554. I'm going to go ahead and rewrite those using 0, 1490 and 20, 3554. That way it'll just look easier whenever we're doing our equations. So again, I already know that my y-intercept right here, whether I'm using a linear function or a exponential function, the y-intercept will always be the same. So a equals 1490, because again, that's the y-intercept. So I already have y equals 1490 b to the x. Perfect. Let's figure out that b. And again, we're going to figure out that b by using the second coordinate. So that will be, let's plug in our y value, 3554 equals 1490. B to the, what is the x value right there? It would be 20. Ooh, that's a big exponent. Let's see how we can handle that. Well, let's go ahead and solve for b. Well, 3554. There we go. 3554 divided by 1490 equals b to the 20th. Well, what is 3554 divided by 1490 equals 2.385. So I'm going to do 2.39. You know what? I'm not going to do that. I'm going to write out the whole thing. 2.38523 equals b to the 20th. Now, it is very, very, very important that you do not round this number, this 2.38523, when you plug it back into your calculator. Otherwise, you will get the wrong answer. So again, I know that I can do b equals, I'm going to take the 20th root. So 2.38523 to the root 20, which is the same thing as 2.38523 to the 1 over 20. And this will be much easier to type into your calculator. So so this to the 1 divided by 20, and that will be equal to 1.04442, which I'm going to say that that's approximately equal to 1.04. I'm going to round it to 2 decimal places. So if b equals, remember, a is 1490 and b is equal to 1.04, then my equation is g of x equals a b to the x, so 1.04, nope, silly me, 1490 times 1.04 to the x. And that is the exponential equation.